All right, welcome everyone to lecture 47. So, we have been looking at small signal measurements. So, today we will continue on the discussion. So, last class we have seen how to measure the displacements. If we understand how to measure displacements and small changes in measurement of displacements, we can force an input voltage signal which is also small signal, and then we can estimate the piezoelectric coefficients, which also can change as a function of voltage, but that does not matter, right, because now my technique is so can just capture the dependence of these properties on the forcing function and not necessarily time. So, it isolates the time dependence from voltage dependence. Okay. So that is what we did, which is different from large signal measurements, which actually capture the time dependence of everything, right. So, the properties time dependence, the causes time dependence, the effects time dependence, right. So small signal measurements are preferred way of measuring properties, right. So if I want a direct estimation of properties and simply as a change in cause by change in effect by change in cause, I am going to use small signal measurements. Okay. So let us again look at this time, so we look at how to measure the capacitance, right. So we go back to Q equal to CV, right. So let's close the loop, and so I am going to actually I am applying V equal to VAC VDC plus VAC sin cos omega t, right, C of V, and so we saw this in the last class, and I am going to do what dq is, and I am going to look at what dV is, and that is my C of V, right, essentially. Okay. Now, I am supposed to do this, right, ideally, but it turns out let us see dq. Okay. So dq is C of V times omega times VAC sin omega t. This is what I should measure, right, and dV I know what it is, right. So, dV is equal to omega VAC sin omega t. Okay. But there is a small caveat, right. So, I have a capacitor, I have a plate, right. So, this is specific to measurement of capacitance, right. So, if I am measuring strain, if this is not dq but d displacement of the membrane, right. So, displacement meaning mechanical displacement of the membrane, I can use a laser interferometer and directly measure the displacement, right. So, direct measurement of displacement is not an issue. Okay. Whereas, what I can measure in this electric circuit is I can put an ammeter, right. What is easy to measure is I apply voltage or any voltage waveform, and I measure current through the ammeter, right. So, I do not I do not say it is not possible to measure charge. You can put some sort of an integrator circuit after the current, after the ammeter, and measure charge. But so the most obvious measurement that one can do electrically is I apply voltage, measure current, or I apply current, measure voltage, right. So, let us just think very simply, if I apply voltage and measure current, right, then so I have to actually measure the current and not the charge directly. Then I so if I measure current, right, so I am going to say what I am going to measure is actually dq by dt, and dq by dt is omega C of V, right, VAC sin omega t. This is dt. Okay. So, this part I can measure, right. So, and dV by dt, that also I know, this is dt is omega VAC sin omega t, right. Okay. So, now if I am charging a capacitor, so so okay, I measure the current. So, how is the current going to be as a function of voltage? So, sorry, as a function of time, right. So I have voltage versus time, this is voltage versus time. voltage versus time, if it's a cos omega t dependence, right. So, let me not worry too much about the DC component. So, it is a cos omega t dependence. So, at 0 time I have some voltage. So, it is going to go like this, right, and I am measuring current directly, and current versus time is going to be a sin omega t dependence. So, it is going to go to maximum here, right, and it is going to go to 0 here again. So, it is going to go to maximum when this goes to 0, and it is going to go to 0 when this goes to maximum, right. So, and so on and so forth. Right. So, that is 0 and so on and so forth, right. So, current versus time, is some sort of, so if I have voltage versus time which is going as cos omega t, this is voltage versus time. So, voltage equal to V naught cos omega t, current will then be I naught cos omega t plus pi by 2, right. So, there is going to be a phase. So, this is what is called the phase, right. So, current leads in phase with voltage by pi by 2. That is how this is called. Okay. Then if I actually plot, what is my, so when voltage is 0, current is maximum, right, and right. So, when voltage is 0, current is maximum, and when current is 0, voltage is maximum. So, this sort of, if I draw V versus T, this sort of looks something like this. Sorry, V versus I. My IV diagram of a capacitor, right, at some sort of an AC frequency, right. So, at a frequency omega AC looks like this. This is at a given frequency. Okay, it's this ellipse sort of a curve. Okay, good. Now, how do I get charge from here? So, I measured the current. So, current is measured. I indeed have a dependence of current with time. Current with time is going like this. Right. Then how do I get charge? Charge is nothing but Q equal to integral I dt. So, I have to integrate this curve, and when I integrate this curve I get back my cosine dependence. Okay, that should be 0. And this should be maximum, that should be 0, this should be maximum. So, okay, let me just draw all these. This should be maximum, this should be 0, this should be maximum, and 0. Okay. So, this is going to be my charge versus T. Okay. So, this is how I measure charge. I measure charge by first measuring current and then integrating current, right. So, I measure charge, not, it is not some sort of a direct measurement, by measuring current and integrating it with respect to time. Now, this integration can be done using a hardware integrator, what is called an integrator circuit, right, or I can just do it in software, right. So, I can just it's easy, right. So, I just need to do this calculation I dt. So, this I can do it on software, right. So, I mean, if you want to be very precise in charge measurement, you want to use a charge integrator, but so if I have large enough currents that I can do this, if I trust my current measurement, I can just do this integration on software. Okay. So, the charge measurement or the capacitance measurement has slightly more details than let us say a piezoelectric measurement, because in piezoelectric measurement I can directly measure the displacement, right. But in capacitance measurement I would not be able to directly measure the charge, I would measure the current rather, the differential of charge, right. And then using differential of charge I can measure the I can integrate that and get the charge. Okay. So, I will measure current and I can get the charge. Okay. So, that is the small difference. However, okay, so now I have a black box, right. So, okay, so from now on I am just going to come and use what is called a complex notation, right. So, I am going to take V equal to, instead of saying V naught cos omega t, right. So, a small signal, I am just representing VAC, right. So, the small signal V, instead of writing it as V naught cos omega t, I am going to write it as V naught e power minus I omega t. Now, what is e power I omega t or minus I omega t? That is equal to cos omega t minus I sin omega t, right. So, I am going to take the real part of this whenever push comes to shove. Okay. But there is some advantage of using complex notation, we will see very soon what is this advantage, right. So, it easily encompasses what is called the phase, right. So, this omega t plus phi and other things, right. So, that I get from here, for example, omega t plus pi by 2, right. So, the complex notation has a way of encompassing it quite nicely. Okay. Okay. So, I am going to get to the complex notation very soon, but first so okay, now since I am anyway measuring current, right. So, I am going to measure current, apply voltage. I do the same measurement if I have a capacitor, I do this measurement with a capacitor, but I also do the same measurement with a resistor. Even in resistor I can just apply a voltage waveform which a cosine this is V equal to VAC cos omega t, or let me write VAC equal to V naught cos omega t, and I can measure current, this is V as a function of time, and I can measure current as a function of time which actually follows the voltage, right. Let me cheat a bit because I am bad at drawing things. So, current is also exactly going to be the same as okay. So, current, because current equal to GV, right. So, it exactly follows the voltage, right. So, now what is the phase difference between current and voltage here? So, V equal to V naught cos omega t and I equal to I naught cos omega t plus 0, right. So, the phase difference between voltage and current is 0. So, when I am doing this dynamic measurements, right, I follow the phase, right. So, in some sense I look at the response, the current, which is the current now, right. And if current is equal to I naught cos omega t plus phi, right, if phi equal to pi by 2, I call it a capacitor, and if phi equal to 0, I call it a resistor. There is an inductor also, we do not talk about inductor. Okay. So, this is what some sort of electrical signals, so if I did some basic electronics engineering, I already know all these things, right. So, this is what is called a phasor notation, and the phase between current and voltage changes, right. So, depending on whether I have a capacitor which is an energy storing element or a resistor which is an energy dissipating element. Right. So, how does I versus V in a resistor look like? It looks somewhat like this, right. So, it is a linear resistor, right. So, IV is Ohm's law, right. So, Ohm's law is followed. This is for a resistor. For a capacitor it looks somewhat like this. This is for a capacitor, this is I versus V of a capacitor. Okay. All right. It is impossible to find devices which are pure resistors or pure capacitors, right. So, this is what electrical engineering has already taught us, right. It is not possible to find ideal capacitors or ideal resistors. So, when I actually, now how do I know that? When I actually apply V versus T, which is a nice cosinusoidal waveform, and I measure I versus T, I generally get phase differences which are neither pi by 2 nor 0, right. So, I have I equal to I naught cos omega t plus some phi, and this phi can be anywhere between 0 and pi by 2. Okay. So, that means that phi equal to pi by 2 is a capacitor, phi equal to 0 is a resistor, but phi is anywhere between 0 and pi by 2 is so I have both a capacitor and a resistor, right. So, that is how electrical engineers interpret this, right. In fact, the equivalent circuit for that will be I have a resistor with conductance G and I have a capacitor in parallel with capacitance C, right, and I apply a voltage an AC voltage across that, right, and then I measure the current, right. So, that is the ensuing current. No, okay, so this arm is not necessary. I measure the ensuing current, right. Okay. So, so these are the sort of measurements that we do. So, if you did what is called an impedance measurement and paid attention to what it did, you are actually measuring current, right, as a function of time when you apply voltage, a small signal voltage, as a function of time, right. And so your voltage now I am going to change to a complex notation is varying as e power minus I omega t, whereas your current that you are measuring is not is actually going to vary as e power minus I omega t plus there is going to be some phase difference, right. Now, this phase difference tells me what is the value of capacitance and what is the value of G, right. So, depending on the value of G and C, I can adjust this phase difference, right. So, based on that I can estimate what is the conductance, what is the capacitance, right. So, one measurement, one dynamic measurement is giving me both G and C. G is the dissipative property, it talks about charge dissipation, G is actually 1 by R, right. So, R is the resistance, G is the conductance, okay, and C is the energy storing property or a conservative property. It talks about storing energy, right. Just one dynamic measurement, right, has two components, has two faces to it, right. So, one side is the capacitance, the other side is the resistance or the conductance, right. So, I do not need to do two different measurements, I can just look at one dynamic measurement. If the charges are moving so if the current is in phase with voltage, that is capacitance, if the current is out of phase with voltage, that is conductance, right. And so if the current and voltage are not exactly, the current is not exactly either completely in phase or completely out of phase, there is some phase difference, right, then I can always say that the values of G and C, right, so determine what that phase difference is, and as a result I can estimate what G is, what C is, right. One measurement is giving me two sides of the same coin, right. One side is G, a dissipative property, and the other side is C, a conservative property. Okay. So far we have been thinking of them as two different properties, but now we know that so one measurement is giving me so two different properties, right. So let us build on that. Same thing will happen even there is no perfect piezoelectric material, right. So if I look at a piezoelectric material, so I apply voltage, sorry, even in a piezoelectric material, I apply voltage as a function of time, right, and I measure strain as a function of time, or this is electric field rather, and I measure strain as a function of time, and the strain does not need to be exactly in phase with voltage, right, but the strain can shift, right. So, the strain can be slightly out of phase, there can be some phase difference, x equal to x naught cos omega t plus phi, whereas E equal to E naught cos omega t, right. Now, the part of this, or if I write it in what is called a phasor notation, E equal to, or in terms of this complex notation, e power minus I omega t, whereas here x equal to x naught e power minus I omega t plus phi. Okay. So, if I write it in this complex notation, let's look at x is eventually supposed to be d times E, where d is my piezoelectric tensor, right. X is x naught e power minus I omega t plus phi equal to d times E naught e power minus I omega t. I just said x divided by d, x naught, or the amplitude of x variation versus the amplitude of d E variation should give me the piezoelectric coefficient in a small signal measurement. So, in the small signal measurement scheme, so I have d equal to x naught by E naught e power minus I phi. Okay. Now, if I look at what d is so this one I am going to call it as some quantity, I do not know. So, let us give it a name. So, piezoelectric tensor, right. So, that is what I am looking at. Okay. So, this I am going to call it as d amp, right. So, for a reason. So, I am going to say this is the amplitude, right. So, this is the d amplitude e power minus I phi. Now, if I expand this, this will be d amplitude cos phi, right, minus I sin phi. All right. So, what do I have here? So, now d has a real part and an imaginary part. The real part is given as d amplitude cos phi, right, plus the imaginary part is given as d amplitude sin phi. Okay. My property, I am putting off this phase difference in the property itself, right. My property has a real part and an imaginary part, right. Now, this real part, right. So, if imaginary part is 0, that means phi equal to 0, right. If imaginary part is 0, then so this is a very conservative property. D real is a conservative property. Here I have x follows E, x is in phase with E. This is the in phase component, right, or this is the conservative component. Similarly, if I look at Q, right, so Q is a charge, Q will be C V, right. So, in some sense, now I'm if I okay, so if I measure so I will have a real part of capacitance plus imaginary part of capacitance times V. Okay. Now, if Q follows V, I have a capacitance. I is so current has a phase difference of pi by 2, and that means Q has a phase difference of is in phase with V, right. So, that means I have no dissipation. In other words, if the cause exactly follows the effect, nothing is dissipated, right. If the effect is in phase with cause, there is going to be no dissipation. But so if so cause being Q, right. So if Q, however, in case of a resistor, right. So in case of a resistor, Q does not follow V. Q is actually pi by 2 separated from V, right. So, Q is pi by 2 phase lagged from V in case of a resistor, right. So, earlier I was talking in terms of I follows V in case of a resistor, but let us go back to the conjugate thermodynamic quantity which is Q, right. So, not really I, not really the flux, because we said every time charge is moving. So, now definition of flux becomes a bit tricky, right. So, let us go back to our original thermodynamic quantity Q, and let us see what are the dynamics of this quantity. If Q's dynamics are exactly the same as V's dynamics, if Q is following V, right. So, Q is in phase with V, then I do not have any dissipation, but Q is not following V, V is going up, Q is going down, and so on and so forth, then I have a dissipation, right. So, does not follow V, then I have dissipation. Okay. Now, I am going to write this as Q equal to C C real plus I times C imaginary, right, times V naught e power minus I omega t. Okay. So, this is the forcing function. Okay. So, then that is equal to Q equal to C real V naught e power minus I omega t, right. This is the in phase part plus C real I times C real V naught e power minus I omega t. Now, if I have an I is nothing but e power minus I pi by 2. So, that is equal to Q equal to C real V naught e power minus I omega t plus C so this is C imaginary V naught e power minus I omega t plus pi by 2. And we said this is the in phase part, this is the out of phase part. Okay. So, this gives me dissipation and this gives me energy storage. In other words, it is, if I write C as C real plus C imaginary, the imaginary is telling me about dissipation, or imaginary is telling me about the resistor component, right, and the real part is telling me about the conservative or the energy storage component, right. So, every time you can so there is nothing called an ideal capacitor. So, there is nothing where C is just C real, there will always be some leakage or some imaginary part, and this imaginary part of the capacitance tells me how resistive or what is the resistance in the device, right. So, both of them, now if I do this complex notation and write C as C real plus C imaginary, or in general any response function as a response function has a real part plus an imaginary part, right. Even D33 we wrote it the same way, right. So, D real plus D imaginary, right. So, the real part tells me the conservative the thermodynamic part of this function of this property, and the imaginary part tells me the dissipative part of this property, right. Now, if it is electrical, this is conservation of charge or storage of charge, this is wastage of charge into heat. If it is mechanical, this is storage of mechanical energy, this is wastage of mechanical energy, right, into heat. If it is electromechanical, this is storage of electromechanical so energy is stored both in electrical and electrical energy is converted to mechanical energy. This represents a complete conversion, lossless conversion, whereas this would represent a lossy conversion, right. So, there is all loss towards Joule heating, etc. Okay. So, as a result using this complex notation and then transferring all this complex notation to the property is quite useful, right. So, we have the same property. Again, I said it is one coin, heads and tails. Heads is the conservative part, tails is the dissipative part, right. So, one property, complex property, if I write it in form of a complex notation, right. So, I have the real part which is a conservative part, I have an imaginary part which is the dissipative part, right. So, everything then becomes very simple. I can see both conservative part and the dissipative part, right. So, how both of them are affecting my device in the same property, right. So, I can do one experiment which is like I said a small signal small signal voltage and measure current. I can get both the conductivity and the capacitance, which is both of them are part of this complex capacitance, right. So, complex dielectric constant or complex capacitance. Okay. So, with that we are going to now build towards actually looking at so both these dynamics come from charge dynamics, right. So, both complex capacitance and both the real part of capacitance and the imaginary part of capacitance. So, the question then appears whether these properties are related, right. So, is there some relation between the imaginary part and the real part, or is it just a matter of convenience that I put them as one complex number, right. Okay. So, we will not answer that question right now, we will start answering that question in 2 to 3 classes from now, but right now so with that background let us actually look at so let us build it up to there, let us look at actually more dynamics, right. So, atomistic dynamics of let us say one of the properties, and one of our favorite properties is dielectric constant, right. Let us look at atomistically, I keep saying charge fluctuates, but what is the nature of this charge fluctuation, how does it change with frequency, right. So, since it is dynamics I should keep changing the frequency and see what is happening. Okay. So, let us do that first let us look at the atomic picture of what is dielectric constant. That is one example that I am going to take in this course, and then actually explain you the atomistic origin of it, but every other property will have a similar atomistic, we will have some sort of an atomistic origin, right. So, in this course we are not going to do property by property and say this is the atomic origin of this property, this is the atomic origin of this property, but so the framework is general, the atomistic details can be different, right. So, that is something that I want you to appreciate. Okay. Okay, so let's start by looking at what are the atomistic dynamics of a dielectric dielectric constant. If I have Q versus T and for a given voltage versus time, if there is some phase difference, right. So, voltage versus time is a cosinusoidal profile like this, whereas Q versus T is not exactly so it lags or it leads in phase a bit, or it lags in phase, right. So, let us just draw it like this. Right. So, there is some sort of a phase difference, right. So, this phase difference is phi. Okay. Now, if I have to plot, this is Q versus T. Now, if I ask you to plot, so this is almost a very good capacitor, this is almost ideal capacitor, but there is nothing like almost ideal, right. It is either ideal or it is not, right. So, there is nothing like ideal capacitor, but the phase difference phi is very small, right. If the phase difference phi is very small and I ask you to plot how Q versus V looks like, right. So, for an ideal capacitor so if so let us ideal capacitor Q versus V is going to be a straight line, right. So, because Q exactly follows the phase, right. So, of V. If it does not exactly follow the phase of V, right. So, Q is actually peaking at slightly lesser voltage. So, I go up to this voltage, let us say. So, this is the maximum value of Q, so this is the minimum value of Q, and maximum is happening at this voltage, right. So, Q is here at voltage equal to 0, and then Q starts increasing, and voltage is also increasing, voltage keeps on increasing, but then Q would start to decrease at some point, right. But still voltage is increasing up to this point, and then so voltage then starts to decrease and Q is also decreasing, right. So, then voltage goes to 0, Q goes negative, which is happening here. When Q goes to 0, voltage is still positive, that is this point, right, and this is how it looks like, right. So, generally if I just measure charge, right. So, on any regular capacitor I do not see these straight lines, rather what I see are curves like this, right. So, this is Q versus V, right. So, this area under this tells me that this is actually a bit lossy. The hysteresis in Q versus V tells me that what I have is a lossy capacitor, right, and you know the area under this gives me the dielectric loss. And why is dielectric loss happening? Because the capacitance is not, you know, a completely real quantity, or the dielectric constant, right. So, dielectric constant is epsilon real plus imaginary epsilon, right. So, the imaginary epsilon gives rise to this opening of the loop, right. So, this is what gives rise to the hysteresis in Q versus V. Okay. So, this is something that you may want to keep in mind, right. So, whenever there is a phase difference, I get these sort of you know, so what is supposed to be a straight line is no longer a straight line, it becomes this sort of lens like shape. Okay. So, for all the linear properties, same thing, I can also measure you know D33 as a function of voltage, right. So, ideally if D33 is completely, you know, if lossless, if the material is completely lossless, I should get this sort of a D33, but there are always losses. D33 is actually going to be D33 real plus D33 imaginary I times this, or in other words I can also write it as D33 amplitude times e power minus I phi, right. So, it is a complex number, and this phase difference, or you know, which is non-zero phase difference, or the imaginary part actually gives me something like this, right. So, this is a real material, always this is the ideal material. Now, instead of D33, or you know sorry, not D33, this is displacement or strain displacement delta, right. Instead of delta or you know Q, I can you know replace it with any sort of property, any sort of effect. So, I am just going to call this effect, and instead of voltage or temperature or whatever, I can call this cause, right. So, any cause effect relation, and these are, you know, thermodynamic causes and effects, not fluxes really. Okay. So, this is force and this is the cause, the you know, so the thermodynamic cause of force, those are going to, if they are, you know, so those typically tend to be this in a linear regime, those typically tend to be like this, and this any sort of hysteresis, they tend to be hysteretic, and hysteresis indicates losses. Okay. So, keep that in mind. So, if there is hysteresis in cause and effect, and these are thermodynamic causes and effects, right, that means there is an underlying loss that I am not considering. Take any thermodynamic property, what we studied as thermodynamic property, there are no ideal thermodynamic properties, there are always losses that come in, right. So, and I can just measure cause as a function of effect. If it is, you know, if it is hysteretic in nature, then that means that there is some underlying loss process that is happening. Okay. Okay. With that, let us go back to the atomistic picture of dielectric constant, and we will build towards a complex dielectric constant. Okay. So, I think so right now I am running out of time in this class. So, probably this will be a good point to start in the next class, right. So, we will take you know, so it one step further, and we will see actually what will happen, what is atomistically, how is this dielectric constant coming, and what does it mean that it depends, you know, what does it mean that there are dynamics of you know dielectric constant, how does it depend with frequency, how does it depend with time. So, all these questions we will ask, and then we will actually you know say that all the other properties also will behave quite similarly at a big picture level, but the atomistic reasons for these dynamics can be different. It can be, one can be mechanical in nature, one can be you know chemical in nature, but overall that the mathematical structure would remain, right. So, for all the properties. Okay. So, with that, let us end this class here, and let us take it up in the next class. Thank you.